Oh, what's going on? Memes here. So we're back. It's a little bit of a broadcast following up on the segment I took from a discussion that came out publicly recently that I had actually been fortunate enough to attend back in, what was it, July 2nd. I know it was July 2nd because, well, that's when it was dated on the Discord server. Um, this is available on the Wolfram Institute YouTube channel and everything. Feel free to link it to the doobly doo below. I tried to I downloaded the original source file and tried to clip out of it because it's on the Institute website. It basically I tried to upscale it as much as I can because we were using the was it Bentley University just standard Zoom conferencing. I think it's either normally like 720 or 360p or something like that. You can make it out, but we're going to be going over about the 18 minutes or so. That should be more than enough to fill up an hour of Professor Barandas's flowchart. And it's interesting because he happens to be a philosopher of physics. He happens to be part of Harvard's Department of Physics and stuff like that. So it's like, listen, hey, I come on and say a random thing. Maybe it's true, maybe it isn't. It's like, I'm going to do it on the internet. Professor Barandes is he seems to be a well-respected philosopher of physics, and he would argue that if his indivisible stochastic processes do end up holding water, he would prefer to be referred to as a philosopher because he's like, well, I know physicists will just call me a physicist. So, that was a behind-the-scenes remark, something that for some reason I'm sharing here, but let's get into it. Yes, Jolly Duck, welcome. Happy Spooktober, my friend. Stay spooky. All right, so let's bring this up here, and we have a quote that I love. At one point, he said, "It's like nobody will be able to escape my flowchart." So let's start with this. As we can see, this is Jacob Barandes' flowchart.
Well, no one's going to be able to escape my flowchart. Flowchart time. Here's our first box. Is quantum mechanics wrong? No. Could be wrong.
Okay, so just to highlight what he's discussing here, basically, you'll hear things along the lines of, and again, I am not a quantum mechanic. I do not have a PhD in physics. Take everything I say with an entire ocean of salt. But the general thing that he's communicating here is, okay, there seem to be different interpretations of quantum mechanics. What the heck is going on? You'll hear things like the Copenhagen interpretation, the Everettian interpretation, and everything. You'll hear all these things. And the reason why he does this, and he'll get into it in a few minutes here, is that if you're trying to explain something to someone, it's like, okay, you can say things, and then they'll hear things, and then people will interpret them in their own ways. So at one point, he's like, all right, let me just start going about a flow chart, because at some point you need to give an answer for one of these things. So it's like, okay, this is what you particularly believe there. Stephen didn't have to raise his hand because he already had thought that there was a little too much that went into it, but that goes to the von Neumann axioms, which I think I'll probably clip out at some point later, because apparently my reaction to being I think I had read over like the von Neumann axioms from like Wikipedia or something like that. I don't know, like 6 months ago or something like that. Um, but he's laying it out in a very straightforward way, and my reaction was, that's crazy. Stephen Wolfram may or may not agree with some of that, but let us continue. So he's laying out a flowchart for quantum mechanics. So it's like, all right, a lot of these are just yes or no questions. It's like, is quantum mechanics wrong? Could be. Maybe it's wrong. Maybe our theory that has led to some of the most precise predictions to 14 significant digits for the anomalous magnetic moment of the electron. Um, that's pretty damn good. Now, again, That's why the term is the standard model of particle physics, aka generally quantum mechanics, has been verified up to 14 significant digits. Now, up to is a very interesting thing because I used to work for a cable company, and very often you would broadcast internet speeds up to. What does that mean? It means you may get internet speeds up to this point, and hey, maybe it would actually exceed it maybe a little bit there. When you say up to, that also means your internet might also not work, which occasionally might happen. You might have little blips where the internet is going up to 0. Price and participation may vary. I feel like that's some caveat here. Okay. But quantum mechanics has been extraordinarily successful. There seem to be a lot of weird things that start to happen as soon as you start discussing it, but let's continue. Okay, so is quantum mechanics wrong? Yes? No? Maybe so?
This would be the wrong theory. Well, you could say yes. And now you've got a research project on your hands.
Now you just have to redo all of basically quantum theory.
Because where's the fun of that? I mean, I don't have a talk to give anymore. Okay, well, let's say no. What if we answer that question no? Well, okay, quantum mechanics is wrong, so now we have to do something. Do something. Well, so the first question we can ask is, did the quantum state of the box collapse?
Wait a minute, of the box or of the system?
Contents of the content. Rigor, okay.
Okay, so now we're establishing some collapse postulate, some may say.
Quantum state of the contents of the box, did it collapse? Okay, well.
Okay, so let's go back.
Of the box, collapse, did the quantum state of the box collapse?
Okay.
Wait a minute, of the box or of the system?
Contents of the content. Rigor, okay. The contents.
Yes, rigor. Yeah, you want to be very specific, and that's one of the things that Professor Barandes is pretty good at, is being a philosopher, very specific with his words. Does that mean he's infallible? Oh, heck no. Are all fallible. I think the is human or something like that. But, all right. So, if quantum mechanics is correct, because the first postulate, no, it's a little hard to see here. It's basically, all right, is it wrong? All right, congratulations. You need to write a new quantum theory. Okay. For the sake of Professor Barandes' presentation and everything here, he's assuming, okay, something's right about quantum mechanics. Now, it may not be complete, because there seems to be some weird stuff and things going on. But he's like, all right, quantum mechanics is correct, or it's not wrong. It's at least not wrong. And then when you are doing some form of probing into the quantum realm, does said quantum state collapse? Okay.
Thank you. Okay. Quantum state of the contents of the box, did it collapse? Okay, well, we got two options. Yes, it collapsed. But if it collapsed, now we have to answer, well, what if the victim's friend were a marmot or one of those antlions or a tardigrade or.
Okay, so the point there is he was using previously, and again, you can find this all in the thingy below. He uses the Wigner's friend experiment, which is basically an extension of the Schrodinger's cat thing, where it's like, all right, you got these quantum things. It's like, well, nothing happens until we observe it. It's like, wait. But if you've got this state, and again, they use the whole quick zero-level approximation of the whole Schrodinger's cat thingy. The Schrodinger's cat thingy is basically, you've got some quantum state and stuff like that, or some radioactive thingy, and then it's going to decay at one point, but you don't measure it. So you got that cat in the box. It's like, well, did it decay? It's like, well, we don't know until we check the box. It's like, but that seems crazy. It's like, well, the cat is in a superposition of either alive or did. I like Professor Carroll's sleeping gas. It's like, all right, the cat is either asleep or awake. It's, to be fair, as somebody that's had cats for a long time, I'm pretty sure I've seen cats in the superposition of awake and asleep. But aside from that, it seems to be a crazy thing. The Wigner's friend thing is basically it's like, all right, you've got a person or a cat or whatever there. You've got an observer there, but then you have an observer observing the observer, observing the observer. It's like the whole Schrodinger's cat idea was supposed to be basically mocking the whole thing that Schrodinger had come up with. And people seem to take it very seriously. It's like, maybe that is the case. Seems to be some mathematics that would suggest that, I don't know, maybe there's a 2/3 probability of the cat being alive or asleep, or a 1/3 probability of it being awake or whatnot. It's like, okay. Is that satisfactory? Or is that just one of those things where maybe just quantum mechanics, just we cannot understand it? If we can't understand it, then, well, maybe the discussion's over. Seeing as I got about another 50 minutes to go, the discussion is not over yet. But, welcome. Welcome, Charlie. Hello, Rick. Good to see you guys. Kali. Hey, Kali. Just thinking about you earlier. In the box, the hydrodynamic, Kali's commenting, the hydrodynamics of a compressible dielectric superfluid will evolve all QFT from Brownian motion. I don't know about that, but I feel like that sounds like it's in line with Professor Barandes's individual stochastic processes. We'll see. We'll see what makes sense. Absolutely awesome one. Flowing through all, there is balance. Oh, hi Maria. Oh, we've got some more Canadians popping. That's always a good sign. It's where are we? Oh God, it's you fall into the time warp. Yes. I did just post this video, but I feel like just posting this video. Well, number one, it should warrant some discussion. It was also the easiest. I was going to do the whole von Neumann axioms. I think I'm going to have to do that in a multi-part video. Just because as he's going through the von Neumann axioms, you just sit there and you're listening to it, and it's like, okay, I understand. You're trying to encompass what existence might be. So it could be n-dimensional, which n could be infinite. And I'm just listening to that, and I'm like, that's crazy. But again, it's like you're trying to encompass the maximum things. Von Neumann was a freaking genius and stuff like that. So it's like, all right, you're trying to encompass all these things. And to sum up Professor Barandes's general thing, and we will get to his thing at one point or another. I do have his paper linked in the doobly-doo. I do need to still finish going through it. But the general idea is the past matters. I mean, I know, imagine my shock. It's the whole, when he says, apparently the keyword is Markovian. What does that mean? You take a snapshot. And then you assume that's like time zero. And then for every iteration of time, more and more stuff and things are going to be going on. But we can predict, given the state, if we were to know everything at that particular point, we should be able to figure out what's going on. Apparently he didn't hold to that assumption, and things got really weird in that quantum mechanics, so to speak, seemed to make sense. I.e., you can't just take a snapshot. Basically, it's non-Markovian. So the concept, and again, I'm not a mathematician, the concept is the past matters. If you wanted to have perfect predictive powers, you would need to know everything that's happened before that point, up to that point. Then you take all that information and you could theoretically be able to perfectly predict what's going on, and apparently all the weirdness of quantum mechanics seems to go away. Stephen Wolfram at one point, he said, so you've basically front-loaded the problem. You just need to know what everything that happened before that. Whereas it sounds like you do the standard quantum mechanical Markovian approach where it's like, all right, we take this state, we move forward, and all this weird stuff seems to happen. So it's like, I remember when Stephen Wolfram had said that, I'm like, wait a second. So he's front-loaded the problem, meaning you would need to know everything that happened before in order to properly predict or see what's going to happen in the future. I'm like, isn't that like the definition of computational irreducibility? Like, you need to do everything up until that point to see what's going to happen next. It'd be really cool if those guys sat down for a discussion. I think that would be pretty neat. Let's see. Let's continue. Continue, Professor.
A single cellular organism or a virus, like an electron. Do they all collapse?
You're replacing the observer with an arbitrary,
so
another form of life.
then we have to this ambiguity problem, and this is called the measurement problem. What exactly counts as a measurement? Well, this is actually a little bit too quick. This isn't quite right. We actually have a question that comes out first.
What's a measurement?
Was it due to the measurement? Is the collapse due to the measurement? Well, in that case, we have this box to answer. What special magical properties do measurements have that make collapse happen? If it's not due to the measurement, well, then it's due to something else. This leads to a class of theories called dynamical collapse interpretations. Theories.
So
GRW is the most famous. Girardi, Rimini, Weber initiated this in like the 70s, I think. The idea is there's some mechanism that's just spontaneously making quantum systems collapse when they have too many degrees of freedom. Not
okay, all right. So stuff collapses, whatever. There's some quantum state. It's gonna collapse from some amalgamation of states into whatever we believe we're measuring. That's what I'm taking away.
Not due to measurement. And this is an active area of research. Some models of dynamical collapse theories have been ruled out experimentally. Some are still viable, but they're complicated. They've got lots of ad hoc constants and parameters in them. I'm not particularly moved by them, but your mileage may vary. Okay? So these are the possibilities. Either it was due to the measurement, and the measurements have some magical properties we have to answer, or not due to the measurement. Now, there is a side problem separate from the measurement problem. Even if we know exactly what a measurement is, here's another question you could wonder. Remember, I said that we talked about this happening. What's happening in the axioms is unitary evolution for undisturbed systems or measurements. Well, what about everything else? Like
what's going
birds
on?
Foraging.
Well, so
People falling in love. What about early gases mixing in the primordial universe? No observers there. The universe is too hot to have observers.
Yeah. What the heck is an observer? Apparently these are things that folks have been arguing about for the past century. I think it literally is the past century now. For the past 100 years, people are like, well, what's actually going on? It's like, well, we're unsure, but we seem to be able to do a whole lot of calculations. Hey man, it's apparently this is how we're able to communicate. I mean, people are able to remotely view, as I'm remotely viewing some digital bunch of pixels from a thing that I was actually at that was recorded by some university thingy via Zoom, and then I re-uploaded, and now I'm playing here. Yes, magic or quantum stuffs. Again, your interpretation may vary. It's I suspect we're not going to see Steven that much for the next month. He's currently doing a European tour, I believe. That's what I believe is going on. I won't mention how I may or may not know that. Occasionally keep in touch. Okay. Let us continue.
If we're not talking about measurements, can we say anything at all is happening according to the axioms? So the axioms give us the resources to say that anything else is happening. Even if we knew these are measurements and these are not measurements.
So what's being measured typically? Is it the states of electrons that are around atoms?
I don't know. The axioms don't say what's typically being measured. The axioms just refer to measurement.
Well, what's
Suppose
typically
we-
being
Suppose we solve the, oh, hello.
You have above position and momentum and energy, so you have some specifics.
Those things, but there could be other things. This isn't an exhaustive list. Not an exhaustive list. I don't know what exactly what a measurement is, what counts, and that's a measurement problem. But suppose we solved it and we said, okay, these things are measurements. When a person comes along and measures electrons, that's a measurement. We know that. Okay, then what?
right? So is that typically what these axioms are talking about?
Yeah.
There is measurements of electrons around atoms?
Or observation
I mean,
of
what-
you, I'm looking at you, photons are bouncing off of you or whatever.
Photons then.
Photons, I mean, all kinds of stuff.
I mean, if we're all just measuring everything, I mean, that kind of sounds some of the things like Bill was saying there. So, is that what's going on? I don't know.
We know some things are
I mean,
measurements.
photons are generated by electrons and atoms moving between discrete orbitals. So are the discrete eigenvalues of this matrix somehow parallel with the discrete energy levels of an electron around an atom as dictated by spherical harmonics, let's say?
Dugan is
There's
an
not a
actual
precise
mathematician.
correspondence between the eigenvalues of the one and the other.
Hold on.
There's not a precise correspondence between the eigenvalues of the one and the other.
Okay.
Energy levels versus other things. For example, energy could be quantized, but position not quantized. The electron position is not quantized, but energy levels are. My larger question is just if you're an early universe astrophysicist and you are writing a paper saying, I believe that when the universe was 500,000 years old, after the last scattering surface, after the universe became transparent and light, I believe that there were electrons bouncing off photons and doing this particular thing. Or I believe that before the last scattering surface, when the universe was so hot that it was a plasma and opaque to light, I believe that gases of hydrogen were mixing in a certain way with gases of primordial helium or something like that. Can you say those things according to these axioms? Do these axioms give you the resources to talk about that happening?
It's interesting that we're renormalizing after each measurement. It's almost like we're treating.
So just to go into a little bit of something. Hold on, let's do this. I think this will actually work. Yay! I'm learning. All right. So a lot of times you hear momentum. All right. We believe we're measuring this thing. We have some concept of momentum. What's momentum? It's just the natural units, Planck thingies, the mass unit. You got some notion of it traveling a distance or a length over a period of time. Okay. So you've got that. All right. So if you're in a Planck unit and now you're going to measure another distance over a time. What happens if you measured the maximum of distance over the minimum distance over the minimum time is probably the best way. I basically just what's the maximum a thing could go? Oh, see, the speed of light. So when you add that, well, you get energy. Why? Because E equals mass times c squared. These are just natural Planck units, so it's like you've got length divided by a time, that's a speed. The maximum of speed is the speed of light. You got both those things squared, times that, boom. You get the Planck energy. That's how we often express things. So that maybe just be a side tangent, but I felt like I should interrupt just playing the dang thing that anybody can watch at any time. So, all right, let's go back over here.
I feel like it's like we're treating the observers like classical systems rather than quantum systems, and we're doing that renormalization.
We're treating the observers like classical systems. So you're not unique in this point of view. Around this time, there was an interpretation of quantum theory that developed and developed significant purchase over the minds of many of the people working in quantum mechanics. It became known as the Copenhagen interpretation. The Copenhagen interpretation is often
Keywords.
Confused with the orthodox textbook axioms. But the Copenhagen interpretation was a specific interpretation. It said observers are classical. And if you want to hear a concrete statement of this, you can read a chapter called The Copenhagen Interpretation in Heisenberg's 1958 book, Physics and Philosophy. Heisenberg didn't start out very philosophical, but he became very philosophical. He read a lot of philosophical works. There's a lovely interview in the early 1970s with the Canadian Broadcasting Company in which he talks about his friendship with Wittgenstein and his confusion trying to get through the Tractatus. And anyway, so he became more philosophical. But he wrote this chapter in this book, 1958, called The Copenhagen Interpretation, in which he laid this out. But you see it's laid out by other people. Anton Zeilinger gave a talk at Harvard, the annual Lee Historical Lecture. And an hour and 9 minutes in, at the end of his talk, he says, here's what I think about quantum mechanics. And he lays out the Copenhagen interpretation. So there's still people who believe it today. The Copenhagen interpretation says that observers are classical. There is classical reality. That is the reality in which we live and which we think, and our brains can only understand things that are classical. And then there is the micro world. And for the micro world, we can say nothing. We don't know what's going on. We can use mathematical tools like the wave function to relate what classical observers will prepare to what classical observers will see. But the wave function doesn't have any physical meaning other than simply relating classical preparations to classical results.
So, again, not a quantum mechanic, but something operators. All right, you got a position operator. I went through some little mini exercises on quantum mechanics. It's like, all right, you got this, and a lot of it just looks like linear algebra and everything. So I'm like, okay, maybe that's why people kind of like it and stuff. But it may say weird things, but the mathematics seems to work, and it seems to have an extremely high ability to determine probabilistically what the heck is going on. Okay, cool. Let's actually get into it.
Now, the Copenhagen interpretation is a giant cop-out. For one thing, it makes it impossible to explain how the classical world could emerge from the micro world.
To be fair, I think I have seen people try to explain this. I think, was it Brian Greene or something? Like, if you take all the stuff there and everything to an observer like us of our scale, it's like, yeah, we're about a meter-ish. We're about, what, maybe like 50, 100 kilograms, something like that. So we're literally on the scale of many of these things for at least our reference units. So the interesting thing is, well, if you're to have things at like minus 35 meters magnitude of stuff going on, or even at 10 to the minus 10, 10 to the minus 15, those are around the size of like atoms and electron orbitals and stuff like that ish. So I'm like, well, that's like, what is it, like a 10 to the minus 10 is like 10 billion times smaller than our scale. Probably gonna look pretty smooth and stuff like that. So it's like, okay, that's kind of the thing. And then you have renormalization. I forget who was talking about that a little bit earlier. That's, I believe, the recipe to go from, all right, we got some classical things and stuff like that, and how do we convert them to being on the quantum scale? Now, if that has gone about that in different ways, like, oh, if I could find some close points for the Planck constants and stuff like that, then I can probably maybe see what's going on, since weird things seem to happen around the 7th significant digit that seems to correspond with about the magnitude of Ampere's constant, which happens to be just Planck mass times Planck length all over Planck charge squared. Which coincidentally, given our units, is currently defined at exactly 10 to the minus 7 for its magnitude. I mean, for a long time, a lot of people thought the speed of light was like 3 times 10 to the 8 meters per second. That's 300 million kilometers per second. That's freaking fast. We didn't get lucky enough. It's not precisely 3. It's 2.9979, yada, yada, yada. Maybe it's like 78 or something. I always forget like the middle couple of digits. I know it ends with 458. It's probably a 0 after that. But, okay. So if the speed of light is there, And then just given how we have things, we happen to get one constant that is exactly 10 to the minus 7. Some may say we did something exceptionally right. Others may say, well, do we actually know it's 10 to the minus 7? I think Rick had sent me something a couple of months ago where it was a link to one of NIST's things, and I've been spending a good bit of time on NIST and CODATA and going through like the history of units, and apparently we have confidence, and I believe what is it? Ampere's law, so to speak. We have confidence to about the 7th significant digit. And we're getting some more and more precision. What happens if it's not precisely 10 to the minus 7? I mean, would that affect other things in our interpretations of other stuff? Now, I'm not saying it's not really dang close to that, but if it was not exactly 10 to the minus 7, then maybe we might be able to explain a lot more things. But I'm sorry, I'm going outside the bounds of this discussion. Let's continue with Professor Barandes' explanation.
Because it simply presupposes the classical world as
We're
an
talking about the
axiomatic
Copenhagen
ingredient.
interpretation.
Everett was very,
Sorry.
this is again
Oh, let's go back.
possible to explain how the classical world could emerge from the micro world. Because it simply presupposes the classical world as an axiomatic ingredient. Everett was very, this is again where Everett is just, he says this very clearly both to Bryce DeWitt and in his long form dissertation. If you take on the Copenhagen interpretation, you're just giving up on the idea that we're never going to be able to understand how to get the classical world to emerge from quantum theory if you're just presupposing the classical world. So
See, it helps when you unmute your mic. So I think that's where you hail the term quantum supremacy or something come from, because, it's quantum and this is just our view of what's going on. Fair enough. Hey, K-Shell. Good to see you. We're just going into Professor Barandes' flowchart, which, to quote him, no one will escape my flowchart. I thought that was a fantastic a quote. Let's see. Well, if you watch it later, I don't know. Did the tree fall down? Did it have a reason to fall? That might be a good question. Well, there's very interesting things that happen on different magnitudes. I feel like it's kind of a little woo-woo. Then again, I kind of do invoke that for a toy model. So maybe it isn't. I'm just saying it's not like the inverse mass expressed in kilograms of the Z boson is like the magnitude of Earth or something like that. There's some very interesting things. Again, I try to follow the calculations in the very best interpretation that I can about what something might mean. If I look at it, I'm like, it's cool. I might bring it up. I might show it like I just mentioned. Am I going to invoke that's exactly how things are? Unless I have a very logical explanation that either agrees with the things that we know and we already believe to be true, or I'm going to have to lay out an extremely well thought out, preferably rigorous, explanation about what's going on, being able to explain more with the same amount of input, or preferably be able to explain more by inputting less and have a clearer explanation than what we currently have. Basically, it's like, all right, you're trying to sell me an idea. Okay. Why should I give up my old idea? My old idea seems to mostly work and everything. My vehicle, it's got a bunch of miles. It's a little clinky and stuff, but it still does the job. Why should I invest in your new shiny vehicle? What is it going to do for me? So, all right, let's see. Well, Poindexter, the crazy thing is, he doesn't come out and say this, but I'm just like, okay. So my general thought about the individual stochastic process, and we'll get into that at a later point. This is just outlining quantum theory and like the choose your own adventure. It's like, all right, do you believe quantum mechanics is wrong? Okay, if yes, then congratulations. You need to develop a new quantum theory. You have a research project. Assuming that it's not wrong, but it might be incomplete per se, because still seem to be some issues. But assuming it's not wrong, where do we go? It's like, all right, well, we go there. All right, okay. Now we get into the whole, does their quantum state collapse? Does it not collapse? What is happening here? And then we're going to go through, and he's going to get into many worlds and stuff like that. And he explains it, and again, it's probably one of the most viewed videos on the Wolfram Institute YouTube channel. Is a lot of the comments where it's like, well, thank you for sharing this. It's like, oh my god, you're like explaining things, and it's like a 4-hour conversation. So he does actually go into some actual mathematical logic and operators and stuff, but his ability to explain things in a way, he's good. So let's let the good professor continue.
I'm not a fan of the Copenhagen interpretation. Very few people who look at it seriously, I think, are. Although a lot of people will simply say I'm a Copenhagenist because they want you to go away. Yeah.
Before you said electrons can't make measurements or something, or can't collapse wave functions. Is that right?
I mean, if I consider a particle physics process in which an electron supposedly scatters off of something, and I keep track of the electron and the thing, there's no collapse that happens. I just get an entangled wave function. I mean, there's one sense in which what's going on in the Bell CHSH example with Alice and Bob, that the two particles did bump into each other, and then they were separated, and there was no collapse of them. They remained in some entangled, unitarily evolving superposition. So you're latching onto real problems here. Okay, so this is our flowchart so far. Okay, yes, if there's collapse, we have a measurement problem. We have all these other phenomena that seem to be happening in nature, like early gases mixing, people falling in love, all that stuff. We think those are happening. But if we take the axioms literally, those are strictly speaking outside the ambit of the axioms. Either we don't believe those things are really happening, or we don't believe quantum theory can describe them, which means we're admitting quantum theory is incomplete theory, or we have to argue that somehow they are in fact measurements somehow. Good luck.
Oh, yes. Muting myself again. But Poindexter, I think that's what I like. And one of the things is he's like Stephen Wolfram in a way. And I think that's why they kind of get along pretty well, is that he's also a really big historian, because he'll start saying these things. And rather than just saying it, like, he gives his citation. He's like, at 1 hour and 9 minutes into his lecture, he's like, well, so this is what I think about like quantum mechanics of the Copenhagen interpretation or stuff like that. Or it's like so-and-so from 1962. And you get a lot of these little bits and stuff like that I feel like he's a person, if you're going to be a philosopher, you're probably going to dig through a lot of history and see what other folks have said, especially if you're trying to be rigorous and thorough. And Stephen Wolfram does that, even for like the Wolfram Physics Project. You look back, it's like, yeah, he's literally like citing like Schrodinger and Heisenberg's original works and everything like that. It's like, okay, absolutely. Well, that's the thing. I'm also just like, well, if the past does matter, I mean that. So basically, in order to have maximal predictive power about what's going on, you just need to know everything from beginning of universe. I think. So in order to do that, you would literally need to play out universe. I'm saying universe with small u. When I say that, it's realm of persistence. Basically, the realm in which we live. The Cool Worlds podcast actually had a interview with Will Kinney. He's a cosmologist. They just put it out the other day. Basically, I'm citing that because one, I think he's an entertaining dude. He might be the only person I've ever seen to like kind of like successfully pull off a man bun. I couldn't do it. But I just knew him as like, oh, he's kind of a science dude that we follow each other on Twitter. And I'm like, I see him on like World Science Festival and Cool Worlds. And number one, dude man sounds like Nicolas Cage. I'm sorry. I think I first started listening, and a lot of times I don't have the picture up because I'm very auditory based, and I'm listening. I'm like, is Nicolas Cage talking with Brian Greene? I look, I'm like, it's Will Kenny. My whole tangent for that was at one point he's like, when I say universe as a practicing cosmologist, he's like, I mean where we live. Maybe there's other stuff out there, the RB dragons, I don't know. But the general concept is, well, this seems to be where we live. Let's try to figure out what's going on. So I tend to agree with him. That was an appeal to authority right there, just to categorize what I was doing. Let's get back to Professor Barandes going over.
Showing that they're measurements. That's a difficult task. Okay. We can say maybe in broad terms, maybe they're, but like to actually show it is very difficult. I call this the category problem. We have this narrow category of measurement related phenomena. We have the much broader category of everything else that seems to be happening in the world around us. And there's a category error of assuming that everything is a measurement, or we deny that all those things are happening. And you could take a very solipsistic view and just say, how do we know anything else is happening? How do we know people are falling apart? How do we know that early gases were mixing? We only know it through measurements. So maybe there really are only measurements. Okay, yes.
Can we say that there's no real collapse? That actually what looks like collapse is just, unitary evolution?
What's your
Then Jean-Bohr.
Jean, yeah, you're anticipating, well, this is a flowchart. We said yes, but we're done with yes. Now it's time to say no. What if there is in fact no collapse?
So really what's happening is that what we call the observer and the observable and the observed system actually are described by one big wave function, and that's the truth. And 3, 4, 5 were just rough
So
approximations.
just take what you just said, but because I'm a pedantic, rigorous philosopher, I'm going to precisify it. Okay? Because people just say this and they wave their, we're gonna be, no one's gonna be.
Yes, because nobody will, describing something that makes them feel uncomfortable, will just start to wave their hands around. It's like, it's literally, I mean, at that point, you're just kind of like doing some wizardry. You're speaking some words. So it's like, all right, you're waving your hands, so you have some somatic component. You're speaking words, so you have a verbal. You got a verbal and somatic component. That's what's required to cast spells in Dungeons and Dragons. At least in 3.5 when I actively played and stuff. If you look at the transcript of this, magic is said a good bit of times in it. I just think that's interesting. It's what he does also have fun, so that is a fair point. Awesome one. Be careful of your analogies. You never know where that might lead us. It may lead to some very interesting paradox. It's very interesting because words are powerful. Words are powerful. I know it seems like they don't have any meaning anymore because people just say a whole bunch of random stuff. But well thought out words, phrases, analogies can help communicate things to our fellow human beings. Because one of the big things we have is they call it noise, where it's like, okay, I say a bunch of words. It may have been completely clear to me. Someone else is like, dude, I have no idea the words that just came out of your mouth. And that actually happens a lot, and a lot of folks, because like we have our own like reference frame, so to speak, where it's like it's completely clear to us. Now, as somebody that thought I might have known some things, number one, when you actually have to explain it and to put into words to communicate to others, that's a different thing than just the thing in your mind. You're activating different things. Now, even if you could successfully express it in a way that's extremely clear to yourself, other human beings don't have your personal experience, knowledge base, and everything, and also aren't in your head. Hopefully. But that could actually try to decode. So you want to be able to explain it in a way, and that's probably one of the big things for like a lot of like these large language models and AI agents like ChatGPT and Grok and stuff like that is if they can kind of get to know you from lots of interactions and stuff, it's like, well, rather than just teaching you the quadratic equation, because well, we just teach you the quadratic equation, was it like 4 mx plus b over 4ac all over blah 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 square root of maybe 4ac. I forget what it is. Rather than just doing that, and having people be like, why? What are some things you're interested in? Oh, I'm interested in science or not business. Okay, maybe we give you a kind of like a simplistic example about something like that. It's like show people things that interest them to get them involved rather than being like, no, listen. I've listened to lectures like that. I've gained value out of people kind of saying those things, but a lot of times I get lost. I don't know, maybe a little too ADD. The logos. Oh, you just went straight into the word itself. I see what you did there. Thank you. Continue with Professor Barandes before I just ramble.
I'm going to be able to escape my flowchart.
Sorry, we got to go back just because this is where I did the initial quote. This was something I think I posted the video. I think maybe I should actually edit this because I actually have like this says it's in 7. Oh God, I apologize. Wow, I had that on far less detail. Okay. Okay, full disclosure, I had another tab on lower resolution. Wow, we can actually read it now. Professional YouTuber. Sorry.
Or just rough approximations.
Just take what you just said, but because I'm a pedantic, rigorous philosopher, I'm going to precisify it. Okay? Because people just say this and they wait there. No one's going to be able to escape my flowchart. In my flowchart. So no collapse. Okay, now we have a question. Follow-up question. There was not collapse. Despite there not being a collapse, was there in fact a definite result of the experiment anyway? Was there still an actual definite unique results of the measurement? Who says yes? Who says no? What do you think?
If you
I think I
generated
said yes.
information, then you made a measurement.
What do you mean generated information?
Well, that would be, you bringing in a word that isn't in anywhere in your axioms, but,
Right.
you know, I guess I would say the definition, which is perhaps circular, is that a measurement generates information and information defines whether something is or isn't a measurement.
That's
Well,
literally circular.
what if we were,
I recognize the voice there. Oh God, I'm sorry, I forget your name, but I've had some discussions. Very thorough, logical individual. Because when he's asking that, it's like, well, what do you mean by information? It's like, well, and he did call Professor Barandes. So it's like, you literally just introduced a word that were not in like the original statement. I believe the Van Neumann axioms, because I don't think they actually address measurement, or maybe they just. I'll go over it. This is a little bit out of order because one, there's a heck of a lot shorter than I looked. I think it might also be close to like a 40 to 50-minute discussion on the von Neumann axioms, because that was about. I think he starts about an hour in and it goes to about the 2-hour mark or so. Yeah, okay, so it's about an hour because this was about 2 hours or so in when he starts going through the flow chart. It was a really long discussion. I mean, man, it was a heck of a time. So, yeah, well, that's the thing. Yeah, no, he did a 3-hour interview with Kurt. Here's the thing. Apparently, Steven knows a lot of people. And apparently he knew of Jacob Barandes. I think he had met him like, I don't know, like a decade or so ago. Um, and then since he was aware of him, they were having lunch or they were eating some dinner or something like that before the actual talk. And there were some people up in the room and they're like, is this talk happening? Where is Jacob? I'm like, Jacob's having dinner with Steven right now, and they're just yakking it up, and then everybody walked over. But yeah, no, it's the amount of history and stuff like that. And what was it? I saw Kurt at MIT's Human Augmentation Summit, and I mentioned, oh yeah, no, they had a chat, and I guess they know each other. So he's like, I didn't know that they knew each other. I'm like, oh yeah, no, it's apparently they had met and they got along pretty well and stuff. So hey, maybe that'll be a future interview that we'll see at some point. I think it would be a fascinating conversation just because they're both so knowledgeable in history. It's like, just get them in the room, go. Might be the easiest interview ever. Just all right.
We're able to like have an apparatus that measured the whole wave function instead of just sampling it at
Measure the whole, what do you mean measure the whole wave function? The axioms don't talk about measuring a wave function. They talk about measuring an observable.
I think that violates no cloning theorem.
Oh, and also, but yes,
Well,
yeah,
that's,
yeah. But that's true, but this is an inevitable consequence of the axioms. The no cloning theorem was proved in, well, there are arguments over whether it was some early no cloning arguments, but usually people assume that it was proved by Zurich and Wooters in 1982, and simultaneously by a philosopher of physics, Dennis Deeks, also in 1982. But that follows from, yes, the no cloning theorem is a formalization of this fact. You can't scan a wave function. Wave functions are not directly observable. Okay, so was there in fact still a unique measurement? If there is a unique measurement, it is somehow not reflected in the wave function because the wave function has collapsed. The wave function is not collapsed, it's some weird funny superposition. If you have a weird funny superposition and one of those is the real outcome and the rest are not, well, then the wave function is incomplete. So if you say yes to this, then the quantum state is incomplete. And this means you've got what are called hidden variables in your theory.
Oh, that's another key word. Hidden variables. Some may associate this. The other keywords that you'll hear as forms of hidden or additional variables, you'll hear things like Bohmian mechanics, pilot wave theory, and stuff like that. Very interesting things. Basically, they're saying that there are other things that we don't know that might be going on. Now, might there be a way to probe that? I'm very biased. That is conjectured away. You might disagree with it, but at least from just a logical foundation about how one might try to go about it, it's the only real two postulates you need are math works, logs are useful. And again, it might, is everything there right? Well, probably not, but it allows one to see a very interesting pattern. And now again, it could be wrong, but at least the logic behind it was at least enough for me to get up and be going to the physics monastery. And I'm actually going to go back out there beginning November. We got a conference coming up, so it should be fun. Got a bunch of other stuff to go over. So where are we at now? We got to hidden variables. Let's see what the good professor has to say about that.
And hidden variables theories are many. There are Bohmian mechanics or the de Broglie-Bohm theory. There's the modal interpretations, of which there are many, and arguably Bohmian mechanics is a special case of modal interpretations. There is the indivisible theory. Indivisible theory.
Which we want to hear about.
Which we'll get, yes, right. Yeah. There are very other possibilities. This is the hidden variables argument. And there's a lot of debate going all the way back to von Neumann, even earlier, but in particular surrounding Bell's theorem about whether hidden variables theories are viable. That's a thing that hopefully we can talk about. So that's if you say yes, there was a definite outcome. If you believe that the quantum state did not collapse and there was not a definite outcome, No definite outcome. Well, then you can ask some more questions. I'm gonna run out of space pretty soon. One possibility is that there were many outcomes. Like every superposition branch was many outcomes. This leads to the many worlds, MWI, the many worlds effort interpretation, with all of its problems, the probability problem and all the various things. You could say, well, maybe there's like a result, but it depends on perspective. I heard perspective mentioned. I mean, cubism is like the perspectival thing, right? These are called perspectival interpretations. The perspectival interpretations, these include, depending on one's view, cubism, although it's sort of complicated because I can't get Chris Fuchs to agree.
I would have said the collapse, yes. I don't go no.
You don't go no. Relational quantum mechanics is perspectival, and there is growing among some quantum gravity people connected with Lenny Susskind, stemming all the way back to black hole complementarity, a similar kind of perspectival interpretation. So could it be perspectival, depending on one's perspective, perspectival or relational? And the relational interpretations say that to Wigner's friend, there was a definite result, but to Wigner, there was not. Like whether there was or wasn't is perspectival. And I'm not going to be able to talk about perspectival interpretations. There are a number of them. There are some pluses to them and some minuses. One is just, what the hell do you mean to say that it depends on perspective whether there.
Okay, again, you say words, it's like, all right, what do you mean by that? That's, to be fair, that's actually just a sales thing as well. When a customer is giving you an objection or something, it's like, oh, when you say this, like, what do you mean by that? And actually probe a little deeper rather than just, you hear words, you make an assumption and be like, oh, well, obviously that must be wrong. Or, oh, obviously I agree with that because that's close enough to fitting in what I can kind of sound like. And even if we don't actually like fully agree, it seems like we agree enough. We can just kind of go through the motions. It's like, what do you mean by that? It's, I don't know. That's asking questions like who, what, when, where, why, how. I don't know. I guess I was indoctrinated into me by Nick News. Nick News, yes. That actually may have been one of the most useful shows that I ever frickin' saw growing up. It's like with Linda Ellerby, actual journalist. I don't even know if she's still with us. But I remember that. It's like, just main takeaway. Just the basic questions. And again, I feel like the basic questions solve a lot of the problems. It's just very often we may pick and choose questions depending upon the situation. Not that people would be biased. We're all very logic-based agents that aren't affected by all these other infinite potential amount of stimuli. Yeah, that would never happen. Okay, so just to go back here, it's like, all right. So, collapse. All right, no collapse. There is no collapse. All right. So, was there an actual definite result? No? Many worlds. Or no? Perspectival. If there was a definite result, and you say yes, you get into hidden or additional variables. There's some other stuff going on that we don't know. Only there was a way we could perhaps probe for a pattern. Continue, Professor.
There was an outcome or not, but there are more sophisticated arguments. And then the final answer is there were just no outcomes at all. I guess we have to include that. And this leads to anti-realism and self-undermining, because if there were no outcomes, then there were no measurements, and then there was no science, and then there was nothing. So pick your place. Where do you live on this flowchart? Everybody should take a stand. Here we go. You ready? Here we go. In double boxes are the terminations, okay? So everywhere you see double boxes, we have terminations. This is a double box. Dynamical collapse theories. Collapse due to measurement. That's a double box. We have hidden variables approaches. That's a double box. We have many worlds. We have perspectival. And I'm not going to ask anyone no outcomes, because if you believe that, you're not in the room. Who says this box
Question about that box though.
Yes.
Collapse, are you assuming the quantum state is a physical thing? that
Well, I didn't say it was
collapses?
physical.
Okay, so just that it
It's, very, very philosophical. It's like, hey, I didn't say that. It's like, well, either I didn't use that language, or, well, maybe it was in the von Neumann axioms. They're very, very broad. Let's continue.
it collapses.
Just
whatever
that we're
you mean-
supposed to collapse, whatever
you
that
mean.
means.
Okay,
Yep.
yes.
Okay, so we got a person here.
Wait, I thought you did say something about collapse. You said that that meant that under unitary evolution, forward from that time, that you would find the same result.
Oh, I did say you'd find the same results, but the question was, am I treating the quantum state
Yeah.
like a physical object?
Yeah,
Oh,
like when he
okay.
says collapse, is there
Didn't
something?
say that. No,
Okay,
I'm,
yeah.
Maybe you have to define collapse then.
I'm being very, very careful with my words. So we have one person for this. Who is hidden variables? Okay, who is many worlds? Who is perspectival? And who, well, no. I'm sorry, you don't get to vote because you don't exist. All right, you have to
It's like, no outcomes. It's like, oh, you don't get to vote because you don't exist. Because, we're obviously not here because it's, you gotta have a little lighthearted humor.
somewhere in this chart, and you'll notice that this is a real problem. Like this, you have to pick a place. When I give talks, before I used to give this flowchart, people would wave their hands and they would dodge and leave. When you show this chart to people, everyone's got to take a stand. You got to be somewhere in this chart. Did anyone not raise their hand? Steven doesn't have to raise his hand. Everyone
No,
else.
I think, I can't unravel where I think I actually am with respect to this.
Okay, okay.
I think
Give
you've
us-
already made too many assumptions
Yeah,
in making this chart.
I am assuming the textbook axioms.
Yes.
And-
I think
and
you're
that's-
crazy.
And
You're
so
totally crazy.
you have gone, I didn't mark the box. Research the function.
That's good.
You're on the chart too. Everybody is on this chart. It is a
Okay, good.
cosmic chart. It was there.
That's within the rule, yeah.
Okay, so, I have to go back for one moment because
But-
y'all may have noticed that, at the end there, Steven made a comment that I think helped relax people a little bit. Where was it?
Everyone's got to take a stand. You got to be somewhere in this chart. Did anyone not raise their hand? Steven doesn't have to raise his hand. Everyone
No,
else.
I think, I can't unravel where I think I actually am with respect to this.
Okay, okay.
I think
Give
you've
us-
already made too many assumptions
Yeah,
in making this chart.
I am assuming the textbook axioms.
Yes.
And-
I think
and
you're
that's-
crazy.
And
You're
so
totally crazy.
is
Okay, so at that point, I'm probably around 2 hours or so in. Stephen Wolfram at one point is just like talking about the von Neumann axioms. His response is, "It's crazy. It's totally crazy." And then people start to relax and laugh and stuff. So let me go to something slightly different. Let's go to the slightly earlier in that discussion because this isn't in the video. Or well, this is in the full video that's on the Wolfram Summer School or Wolfram Institute. Wolfram Institute. Let me just bring it up. Let's bring Professor Barandes. Where are we? Okay. So share this tab instead.
Quite 11. We're having a good time. We're having a good time, right? Okay,
I think you've already made too many assumptions
Yeah,
in making this chart.
I am assuming the textbook axioms.
Yes.
And-
I think
and
you're
that's-
crazy.
And
You're
so
totally crazy.
is
Okay, so it's around 2 hours and 13 minutes in. Stephen Wolfram calls it crazy. All right. Where was that? I think it's about 109. Okay. Well, real quick, we're just going to go over postulate one of the Dirac von Neumann axioms.
laws of motion which axiomatize Newtonian mechanics or the Maxwell equations or whatever it is you're using to add. These are the things that are supposed to play that role according to the textbooks. So this is going to be called textbook or orthodox quantum theory. Now, why do I say Dirac and von Neumann? Dirac formulated these in a textbook in 1930, von Neumann in 1932. 1930, that was Principles of Quantum Mechanics. Dirac was in his 20s.
Wow.
Let that sink in. He was like 25. Von Neumann, it's 1932 in Mathematical Foundations of Quantum Mechanics, although it was a German title, and it's like Mathematic Grundlagen der Quantum Mechanics, something like that. Okay. They formulated these axioms then, and here are the axioms. This is what the axioms say, and I want you to pay attention to what they say and what they do not say. So axiom 1. Axiom 1 is about things called quantum states. A system's quantum state is a positive, semi-definite unit trace, which means it's trace class, operator or matrix on a Hilbert space of some dimension n, possibly infinite.
That's crazy.
That's axiom 1. Okay. Now, if
So I'm just saying about an hour or so before it was officially safe to say the axioms of quantum mechanics are crazy, I'm just like, okay, a system's quantum state is a positive, semi-definite unit trace operator or something on a Hilbert space of some dimension n, possibly infinite. I just listened to that string of words, and I'm like,
That's crazy.
that's crazy.
that's axiom 1.
Yes, I'm just listening to axiom 1. I'm like, that's crazy. About an hour and 20 minutes later, I'm just like, well, yeah. Yeah, that's about all. Hey, we already saw it. I'm just saying, like, my reaction to it just laid on that way. I'm like, I understand why you need to be broad. I mean, you're trying to parameterize reality, but just that string of words, I'm like, that just sounds crazy. And that's why I said it was crazy. And fast forward to another hour or so, having Steven kind of say the same thing and getting people a little bit more open, feeling more open to laugh because Steven, who was an actual particle physicist, and it happens to be Steven Wolfram, basically said the same thing. So I'm like, all right, maybe I'm not just an outcast. It's like, no, you're trying to parameterize all these things, and it seems to have worked really well, but it also kind of leads to very interesting phenomena that seem kind of wacky. And Professor Barandes happens to have some basis for his layout. I'm like, all right, is there a major benefit? Does it help us calculate anything different? Maybe not. Okay, well, what's the benefit? Well, we seem to get rid of that quantum weirdness. Does that mean we can classically represent everything? I mean, I don't know. What does that do? What does that mean for quantum computing if that was the case? I mean, maybe it can still do some very interesting things, but I'm like, is it going to be anything different than we've done a calculation that would take a normal computer 10 to the 35 years to do? And then within the next year, the standard classical computer ends up doing it like in the same, basically is able to do it just about as fast. I don't know. I thought it was an interesting thing, and I always just hold on. Let's go back to our other video. I just at any time I can play this little clip.
Well, no one's going to be able to escape my flowchart. Flowchart time.
I mean, nobody's gonna be able to explain my flowchart. It's a beautiful thing, and he happens to be a philosopher, so he's like, listen, man, maybe it's this way, maybe it's not. I feel like a lot of the scientists that I tend to take most seriously, it's like, could be wrong. Now they may have confidence in things, but it's like, all right, this is the claim. Could be wrong. It's just you have to be careful when some folks really get into things and all of a sudden their mind's like, yes, this is it. And it almost becomes almost like a Gollum thing where it's like, my precious. It's be wary of precious things. I don't know, maybe that's an overall adage. I should stop philosophizing here, even though this was a review of a video about a professor that's working on the philosophy of physics or the foundations of physics. And again, from what I had heard from Professor Barandes, is he considers himself a philosopher first and foremost. And of course, he says, well, if there ends up being any real there, of course, the physicist will refer to me as a physicist, but I just want for the record to know that I consider myself a philosopher. So I'm just passing on the good word. Is the pizza still hot? Oh, is that perspectival? Well, what is hot? Now, one person's lukewarm pizza may be just correct. A person's overly steaming, like roof of your mouth disintegrating pizza may be just right for somebody else. I mean, I like hot pizza. I've also scorched off a lot of taste buds in my time, so all right. Just that's about all we got. So let's that. All right. So long story short is nobody's going to be able to escape Professor Barandes' flowchart. So we're going to do get back into some of the groove of things. Actually, attempting to continue with research rather than procrastinating, getting caught up on all these other things. But that's all we really got for right now. Oh, look, it's 10:37. Huh. What do you know? It's okay. But with that, peace out, everybody. Take care of yourselves. It's a wacky and wild world out there. It's open for a better tomorrow, my friends. Peace out, everybody.